Yesterday we talked about graphing exponential functions. Today we're going to talk about transformations of exponential functions. When we add a constant k to the end of an exponential function, it creates a vertical translation, shifting the graph up or down. The equation of the asymptote is y equals k. Let's look at a couple of examples. For this first example, we're going to use the parent function y equals 2 to the x. I'm going to complete the table, but hopefully at some point you'll start to understand the pattern that's happening for each of these parent functions determined by the base of the function. Here the base of the function is 2, and so we're working with powers of 2. 2 to the 0 power is 1. Anything to the 0 power is 1. 2 to the first is 2, and 2 squared is 4. On the negative side of the table, the y values will be the reciprocals of the y's on the positive side, 1/2 and 1/4. I'll go ahead and start plotting these points on the coordinate plane and connect them with a smooth curve. Because the base is 2, this is exponential growth, increasing from left to right. So this is the graph of our parent function. Now we're ready to compare that to the graph with transformations. Notice that there is a -3 added to the end of the equation. This will shift each point 3 units down. Let's compare this new function to our original parent function, which had a y-intercept of 0, 1, and an asymptote of y equals 0. Our new asymptote will be y equals -3. To create the graph, I'm literally going to place my pencil on each point on the original parent function and shift it down 3 units. The transformed function is the same shape, just moved down 3 units. And the new y-intercept will be 0, -2. For this second example, we're graphing the parent function y equals 3 to the x. The base value is 3, so we'll be working with powers of 3. 3 to the 0 is 1, 3 to the first is 3, and 3 squared is 9. For the other side of the table in the negatives, we'll flip the numerators to the bottom to get 1/3 and 1/9. Our asymptote will be y equals 0. Now, for this problem, I'm going to show you a shortcut because it can become tedious to have to graph every parent function and its transformation by counting up and down to shift the points. So our new asymptote is going to be y equals 1, and it's going to shift every point 1 unit up. We're going to sketch our asymptote at y equals 1, and then instead of graphing the parent function and the transformation, we're going to just directly graph the transformation by plotting the pattern of the parent function, but starting to count from 0, 1 instead of 0, 0. So at -2, I'm going to go 1/9 of a space above the asymptote. And at -1, I'm going to go 1/3 of a space above my asymptote. At 0, which now I'm counting from 0, 1, I'm going to go up 1 unit above that. At 1, I'm going to go 3 units above my asymptote, and at 2, I'm going to go up 9 units. Again, all of these ordered pairs are 1 unit up from the original parent function. So my original y-intercept was 0, 1, and now my transformed y-intercept is 0, 2. Remember that with general form, the leading coefficient a is the y-intercept of the function. So the point 0a will be our y-intercept as long as there are no horizontal or vertical transformations on our graph. So we're going to look at each of these equations and we're going to identify the y-intercept without the transformation of the special constant added to the end of the equation. And then we're going to adjust that number based on the vertical shift. So for just a minute, we're going to focus on b, the number that's holding up the exponent. It's easy to get confused between a and b when there's no leading coefficient shown. So I'm going to identify the b value on each of my equations to make sure that I can find the a value. So for example 2a, my equation has a base of 4, which means the leading coefficient is an understood 1. The y-intercept without transformation would be 0, 1. However, this function has a shift down 2 units. I'll subtract 2 from my y-intercept to give me a new transformed y-intercept at 0, -1. For example 2b, my leading coefficient is 2. The a value is 2, so the y-intercept is 0, 2. This function has a vertical shift down 1 unit, so I'll subtract 1 from my y-intercept, giving me a new y-intercept of 0, 1. Example 3c has a y-intercept of 0, 3 and a vertical shift up 3 units. So we'll add 3 to the y-intercept, giving us a transformed y-intercept at 0, 6. Example D has a base value of 5 and an understood 1 for the leading coefficient, giving us a y-intercept at 0, 1. There's a vertical shift up 2 units, so we'll add 2 to get a new y-intercept of 0, 3. This shortcut can allow us to quickly identify the y-intercept of an exponential function, but only when there are vertical translations. With a horizontal translation, the y-intercept will move off of the y-axis and this shortcut will not work. If we add a number to x in the exponent position, this causes a horizontal translation. It will move the graph left or right in the opposite direction of the sign shown. For the first part of example 4, we're using the parent function y equals 2 to the x. There's no number added to the end of the equation, so the equation of our asymptote is y equals 0. We'll use the powers of 2 in our table to fill it in from -2 to +2. Remember, you may choose to use your calculator to generate a table. Notice that our transformed function has a 3 added to the x in the exponent position. It does not have a constant added to the end of the equation, and so it's understood that the asymptote is y equals 0. The 3 added to the exponent will shift each point 3 units to the left. Now we're ready to graph y equals 2 to the x plus 3. I'm going to start by drawing my asymptote at y equals 0. Then I'm going to draw a vertical line, which is a new representation of the y-axis, and it's going to be 3 units to the left. So I'll draw a vertical line at -3. Then I'll plot the pattern of the parent function, but instead of starting to count from 0, 0, I'll start counting from -3, 0, where my vertical line and my asymptote intersect. So -2, 1/4, then I'll go to -1 and 1/2 a unit above the asymptote, then 0, 1, 1, 2, and 2, 4. I'll connect my dots with a smooth curve to represent a growth function. Let's try it again for y equals 3 to the x minus 2. First, we'll identify the pattern of the parent function, and the base value is 3. We'll complete the table with the powers of 3. 3 to the 0 is 1, 3 to the first is 3, and 3 squared is 9, and the reciprocals of those on the negative side of the table. The equation of its asymptote is y equals 0. Our transformed function has a 2 with the x in the exponent position. The asymptote will still be y equals 0, but this will shift the entire graph 2 units to the right. I'll draw my asymptote and my vertical shift line at +2. Next, I'll plot the pattern for the parent function, but starting at the intersection of my vertical shift line and my asymptote. So -2, 1/9, -1, 1/3, 0, 1, 1, 3, and 2, 9. If graphing by transformations is a challenge for you, you can always type the transformed function into your calculator and graph it from there. Now we'll practice identifying and describing some transformations. In the first example, f of x equals 3 to the x, we see that the change from the first to second equation is that a +3 is added to the end of the equation. This will shift the graph up 3 units. For the next equation, y equals 1/2 times 5 to the x, the transformed equation, y equals 1/2 times 5 to the x minus 4, has a 4 with the exponent up top. This will shift our graph to the right 4 units. The next equation, y equals 3 times 0.4 to the x, is transformed by adding a positive 8 to the end of the equation. This will shift our graph up 8 units. The last equation, f of x equals 4 to the x, is transformed to f of x equals 4 to the x minus 6 plus 5. There are two transformations here. There's a plus 5 added to the end of the equation, and there's a 6 with the exponent up top. The 6 will shift the graph to the right 6 units, and the 5 will move it up 5. Here's an overview of the transformations that we can see on an exponential function. Before we begin to identify the transformations on the function, it's good to start out by looking at the base of the function, which is b, the number that's holding up the exponent. If the value of b is greater than 1, the function will represent growth. And if the value of b is between 0 and 1, it will represent decay. A growth function will start out flat and then increase from left to right. A decay function will start out high and decrease to a flat shape. Next, we'll look at the leading coefficient of the equation. If there are no other transformations on this function, then the a value will represent the y-intercept. If there are other transformations in the h and k position, then the y-intercept will be shifted off the y-axis and a will not be the y-intercept. The number value of a will tell us whether there is a stretch or shrink on the function as well. If a is greater than 1, there will be a stretch, and if it's between 0 and 1, there will be a shrink. We'll look at the sign of a to determine whether there's a reflection in the x-axis. If the value of a is greater than 1, you'll have a regular growth or decay function which will lie above the asymptote. If a is negative, the graph will be below the asymptote. Next, we'll look at k, the constant added to the end of the equation. The value of k tells us a vertical shift. If we see a plus k at the end of the equation, this will shift the graph up. If we see a negative k at the end of the equation, it'll shift the graph down. The equation of the asymptote for the function is y equals k. Finally, we'll look at h, the number that is added or subtracted to the x in our exponent. This number creates a horizontal shift in the opposite direction of the sign that you see. So if you see x plus h, it'll move your graph to the left. And if you see x minus h, it'll move the graph to the right. Once again, let's practice identifying some transformations. F of x equals 3 to the x is being transformed to f of x equals 4 times 3 to the x. The base of our function is 3, and the leading coefficient is 4. Because the base is 3 and the value is greater than 1, this will represent a growth function, and the leading coefficient of 4, which is greater than 1, represents a stretch by 4. The next function, y equals 5 to the x, is being transformed to y equals 1/2 times 5 to the x. We can see that the base of the function is 5, which indicates it's a growth function, and the leading coefficient is 1/2, which tells us there's a shrink by 1/2. The last equation, y equals 0.4 to the x power, is being transformed to y equals 3 times 0.4 to the x power, where the base is 0.4. This represents a decay function because the value is between 0 and 1. There's a leading coefficient of 3, indicating a stretch by a factor of 3. Again, the first thing you want to identify is the base of the function. It's the number that's holding up the exponent. Then that allows you to understand where the other numbers are in relationship to the base. For d, the base is 4, but the leading coefficient is negative, so that makes it neither growth nor decay, and creates a transformation that is a reflection in the x-axis. The next equation has a base of 3, but it also has a leading coefficient that is negative, so it is neither as well. It has a shrink by 1/2 and a reflection in the x-axis. Next equation has a base of 0.8 and a leading coefficient of -3. Again, the negative is a deal breaker and makes it neither growth nor decay. It has a reflection in the x-axis and a stretch by 3. Try these last 3 problems on your own. Then you're ready to move on.